Hey investors, thank you for having me on Squid Tank. My name is Robbie, and today I'll be talking about a possible redesign for a flashlight. This pitch will be presented in three stages. First, I'll be talking about the design challenge and how I gathered and interpreted data into customer needs. Then I will talk about my redesign process, including a predictive sketch and subsequent sketches that led to my final design and why my product is suitable for production. So first, I'll talk about our design challenge. Our Unit 3 design challenge is that I'm working from the perspective of a contractor for a flashlight manufacturer that is losing market share to a competitor. Your supervisor assigns your team this task, understand how your competitor's flashlight works, come up with ways to improve it, and propose a redesign that we can manufacture and market to put our company back on top. So first, we started by having interviews with potential customers about their opinions on this girls trip torch-shaped lanyard pattern crank pig flashlight. Each group member had 3 interviews, which led to a total of 9 interviews to pull data from within my group. I asked them several questions about what they thought of the flashlight's design, what their potential use cases would be for the flashlight, and some suggestions for improvement. I jotted down quick sentences that summarized their answers to my question. Then, out of those sentences, I highlighted the most important words. Green for most important, orange for important, and yellow for nice to have. The image here shows a summary of all the highlighted words in the sentences. These interviews were the baseline for our redesign process. So once we gathered qualitative data from our interviews, we summarized that data in the Zafindi analysis table. In the first column, we stated each of the needs that were mentioned in the interviews. In the second column, we stated how many times each appeared in the data. And in the third column, we gave each need an importance score. The way we decided to calculate the importance score was by simply doubling the frequency of each need. The most important needs that we decided to focus our final design on are making the flashlight brighter, reducing the noise that the crank makes when being operated, having a more efficient crank that produced more power per pull, having a more comfortable grip, being more aesthetically pleasing, having a longer battery life or runtime, and especially being useful in an emergency scenario. We would have focused on all of the customer needs that had an importance score of 18 or higher. However, due to time constraints, we had to compromise on some of the needs. So once we understood what the customers needed, we completed a direct testing process that tested the qualities of the flashlight so we could start finding values that we could later improve on. We decided to do 5 tests. We did a brightness test that tested the flashlight's brightness, a portability test that tested the flashlight's dimensions and weight, a crank loudness test that tested how loud the flashlight was while being operated with the crank, a crank force test that tested how hard it was to pull the crank, and a durability test that tested how durable the flashlight was from being dropped to different heights. The result of these tests can be seen in column 3 of this table. Then, with my teammates, we came up with reasonable improvements for all aspects of the flashlight that we tested. For example, for the brightness of the flashlight, we decided that the flashlight should be around twice as bright at all measured distances, which could easily be done by adding another LED bulb and replacing LEDs with higher voltage, newer LED bulbs, which is what we ended up doing. After we finished our direct testing process, we drew a predictive sketch of what we thought was happening inside the flashlight. My sketch shown here included a large battery that was connected to a circuit board that routed the power to the LED bulbs. For the operation of the crank, which I described as a sort of clamp that held the entire crank inside the body of the flashlight. Once switched, the crank popped out and it was able to be operated. I thought that there were some sort of teeth on the end of the crank that went into some gears, that when the crank was pulled, it would turn the gears and generate mechanical rotational energy. I assumed that since the crank took a little oomph to operate, that there was a gear ratio in order to create more energy from each pull. You can see in the middle of the drawing, I was unsure how the rotational mechanical energy was converted into electrical energy, so I just drew some wires connected to a gear, which I suppose wasn't too far off of how it actually worked. That electrical energy then went through the circuit board and to the bulbs. One thing I noticed from my sketch was that this flashlight feels a little too complicated, and that in my final design, I would want the flashlight to be simpler. So once we finished our predictive sketch, we started designing our flashlight. In concept 1 in the bottom left of the image, We came up with new dimensions for the flashlight that aligned with our affinity analysis on slide 5. We incorporated a larger crank that is more efficient. However, since we made the crank larger, we had to make the flashlight larger in general. Since we made the flashlight as a whole larger, we incorporated a more comfortable grip that aligns with a traditional flashlight so it does not feel awkward to use. Concept 2 on the bottom right is our technical sketch. We incorporated new elements to back up and add to our additions in concept 1. Since we added a larger crank, we subsequently added a larger dynamo to generate more power per rotation while having less rotations, leading to having less noise while being operated. Since noise reduction and durability are two of our key points, we added a layer of insulating foam around the flashlight in order to, 1, reduce the amount of noise that is generated per crank, and 2, strengthen the body of the flashlight from being dropped. It was difficult to draw the insulation on top of the technical components, so we were unable to actually draw it in the technical sketch. Additionally, in concept 2, we came up with a 3-bulb design that utilizes higher voltage bulbs as opposed to the current 2-bulb design in order to produce a brighter light that would reasonably double our light output that we specified earlier. Our final design is a combination of our 2 C sketches from the last slide. For our final design, we determined that the most important item on the list was that the flashlight were to be useful in the scenario of an emergency. Because of this, we decided to address this by replacing the 3 small batteries with 2 AA batteries, which are put behind a removable panel for easy replacement. In an emergency, if the battery in the flashlight dies and the crank doesn't work well enough, well, there's a problem. Everybody has AA batteries in their house for all sorts of appliances, so we selected AA batteries for our flashlight because most people have them in an easily accessible place, making the flashlight especially intuitive in an emergency. AA batteries also have a significantly longer lifespan than the batteries in the original design, hitting on another one of our important needs. For the theme of our flashlight, we decided that a shark would be great, with the crank acting like the shark's fin. The body of the flashlight will be a darker blue, and there will also be little teeth illustrated around the rim of the head of the flashlight to add to the shark's design. Our flashlight is a significantly better product than our competitors because it improves upon several key aspects that customers decided were inadequate. By specifically tailoring the product to be a better market fit than the low-quality pig flashlight, we believe that our product is suitable for mass production. Thank you for your time and consideration for my product.